If you'd
If
like
you'd like
some
some
motivation for
motivation for
studying
studying
electric
electric
potential,
potential,
I'll invite you to look up on Google how
how
much is
much
an
is
electric field meter. You're going to find that they're pretty expensive to get a good electric field meter. By contrast, this little guy, it's called a voltmeter. It can measure potential difference, and things that measure potential difference we all often called a voltmeter. You can get this for $10 or less at Princess Auto. It's cheap and it can measure potential between any 2 points. So if I turn it on, it gives me a reading of 0. I'm going to connect my two leads to two ends of a battery. And it's just a small battery I hauled out of a mic pack. So I put the two ends of the leads on the battery and I get a reading. Sorry, the light just went off in my office. I get a reading of 1.58 volts. That's telling me the potential difference, or electric potential difference, across the two ends of the battery. If I know the potential difference, I can calculate the electric field that exists between those 2 points. I'm stressing saying that we measure across the two ends, and that's true of potential difference in general. You always measure it across 2 points. So let's see if we can use our measured potential difference and find the electric field in our battery.
So let's carry on with what we're doing. We've got the potential difference, which we measured. So because we measured a difference across 2 points, we're going to call that delta V. That was equal to 1.58 volts. The last thing we'll need is the length of the battery. And the length of that battery, I can measure that, and that's about 4.5 centimeters. So we know that the length of the battery is 4.5 centimeters, or 0.0450 meters. We said we'd like to try and find the electric field using the relationship between electric field and electric potential. Well, we wrote down that potential was field times distance. So potential is E times S. That means that delta V is equal to E times delta S. Whatever you change that distance by gives you the change in electric potential. It means that our electric field, this is the strength of our electric field. To write it as a vector, we'd have to think about direction. But the magnitude of our field would be delta V over delta S. Our delta V we measured 1.58 volts. Delta S we measured 0.045 meters. So if we grab our calculator and do 1.58 volts divided by 0.045 meters, we get an electric field of 35.1. Up until now, we've talked about the units of electric field as newtons per coulomb. Turns out electric field also has an equivalent unit of volts per meter. So our electric field is 35.1 newtons per coulomb or volts per meter. If you wanted it as a vector, you would say it goes from the positive end towards the negative end. So there's a reason for studying potential. You can buy the meters real cheap compared to the electric field meters. Let's use our same battery with the same potential, and let's do an electric potential energy example. So let's say in our battery, an electron moves through a potential difference of 1.58 volts. So delta V equals plus 1.58. What is the change in electric potential energy? Delta UE equals. You might remember here that delta U is equal to the charge times the change in potential. So one last little bit we need here is what is the charge? That's given to us in the wording of the problem. It says an electron. As soon as you know it's an electron, you know that the charge that we're talking about is the charge of an electron, which is minus the fundamental charge, or minus 1.6 times 10 to the minus 19 coulombs. Oh, I should have put minus 1.60. I don't quite have room to squeeze it in there. Okay, we know the charge and we know the change in potential, so let's find the change in electric potential energy. That gives us an energy of 2.53 times 10 to the minus 19 joules. Turns out when little charges move through a potential difference, they don't actually change their number by an awful lot, and that's because the charge itself is very small. If we had bigger charges, we'd have bigger changes in potential energy. So let's try and really nail down that relationship now between electric field and electric potential. One thing we really have to think about is to remember that our electric field is a vector and our electric potential is a scalar. So how can we relate a vector and a scalar? That's kind of an important concept and can be a little hard to wrap your head around. So in the picture I have a positive plate and a negative plate, that's called a capacitor. And we know that there's an electric field between the two plates. We know that the positive plate is at a higher potential than the lower plate. So we're building on what we've done before now. And we want to make that relationship. In this picture, our electric field is all in the x direction and it points to the right. So in this picture, our electric field only has an x component, and that x component is positive because it points to the right. So what we see about electric fields in general is that they point towards lower electric potential. So let's take our little charged particle and let's make our charged particle move. Let's make it move along this way. So it moves some distance delta x. And it's going to move because when we let it go, charges will move in electric fields. So let's remember some of our definitions here. We defined electric potential as the magnitude of the field times the distance from the negative plate, which means that a change in electric field would be the change in electric potential would be the field times the change in distance. Or the size of our electric field, I'm going to be really careful here with my notation, would be the size of the change in potential divided by the size of the change in distance. This would give magnitudes. So we know how to find the magnitude of an electric field vector. What about the direction? What about the fact that we're a vector? Okay, in this picture, our electric field is in the x direction. So my component of electric field, I'm going to call EX. I've still got a change in potential. Now that I've got a component, I'm going to start to worry about the sign. Negative is to the left, positive is to the right. So to get the size of my electric field, I do delta V over delta X. What do I know about delta V here? Well, I know that as I get closer to the negative plate, my potential gets smaller. So if my initial was over here close to the positive plate, my final is over here close to the negative plate, I know my V final is less than my V initial. That tells me that delta V is negative. So my EX I know is positive because it points to the right. So my X component of electric field must be negative delta V over delta X, where delta X is my distance traveled. And this negative sign tells me, and it comes from the fact that electric field points towards lower potential. Next, because we're studying physics, why don't we make a graph? We always make a graph. Our electric potential at the positive plate is very high. Our electric potential at the negative plate is lower. Usually we say that that potential is 0. If we draw a graph, we're going to get a linear relationship where the potential goes down as a function of distance. If we thought about the slope of this graph, we would do delta V over delta X. And that would give us a negative number. And then our electric field, let's see, I'm getting ahead of myself here now. So slope is delta V over delta X. Our electric field is minus delta V over delta X. So our electric field is negative the slope of a potential versus position graph. And that's kind of an interesting result that we're going to use a fair bit. Okay, we talked about in the x direction here. On the next slide, we'll look at the y direction. In this picture, I've just turned my capacitor around, so my positive plate is on the bottom. That's where I have my high potential. My negative plate is on the top. That's where I have my low potential. Let's say I take my charge and I let it move in the field, so it's going to move up. This time what we see is everything is happening in the y direction. This is my initial point, this is my final point. My charge moves through a distance delta y because we're vertical, and my electric field is in the y direction. So if we have an electric field that's in the y direction, we see that we get a change in potential as we move in the y direction. So Ey equals minus delta V over delta y. So we don't have to be horizontal, sometimes we can be vertical. So I just said that we get a change in potential as we move in the y direction. Here's an interesting question. What if we had a field that was in an x direction, but we moved in the y direction? What would happen to the change in potential then? Let's go back to our horizontal field here. So my positive plate has high potential, my negative plate has low potential. What if I move kind of straight up? So this is my initial point. I move straight up to some final point. So when I moved in delta y. I didn't move in delta x at all. So what if delta x equals 0? Well, it doesn't look that much like an x there. That's better. Delta y is not 0. And what if our electric field has an x component and no y component? So what happens now? So let's remember what electric potential is. It's the size of the field times the distance. So V initial, our initial potential, is the field, which is all in the x direction, times the initial x distance. So that distance is x. Our V final, our potential up here, V final is our field, which is all in the x direction, times the distance x. X is your distance from the negative plate. You see it when we moved up, we didn't change our distance from the negative plate. So now let's write down what we just saw about our potentials, which is that our final potential is equal to our initial potential. Well, that tells us then that delta V is equal to 0. So the result is if you move perpendicular to a field, delta V equals 0 because you haven't gotten any further away from that negative plate. Let's see. If you wanted to write down that Ey equals minus delta V over delta y, you could certainly do that. You'd have minus 0 over delta y equals 0. So you could do that too if you wanted to, I suppose. The big result, though, is that if you move perpendicular to the field, you don't get a change in potential. Okay, what if we do move with a delta x and a delta y? Let's look at that guy next. Let's stick with our horizontal field. So we've got our high potential at the positive plate, our low potential at the negative plate. And let's say we have our charge and we move up and to the right. So now this is our initial position, this is our final position. So our motion here has an x part. There's our delta x. And a y part. There's our delta y. So what happens to the potential here? So when you move in the delta y, that part of the motion doesn't produce a change in potential. Because that part is perpendicular to the field. When you move along the x direction, there is a change in potential. And we know that that's true because we get closer to the negative plate. So if you don't change your distance, you don't change your V. If you do change your distance, you do change your V. And in this case, your delta V would be Ex times delta X. Okay, so that's what your change in potential would be. Your change in potential would only come from your motion parallel to the electric field. So you only change V when you move parallel to field. So let's just write down our general result. This slide is a little bit full. I think I'll move on to the next slide, next blank one. Now the last thing we'll do is we'll write down the general result. This one tends to get a bit complicated. We're not likely to use this, but I can't really leave it out for the sake of completeness. If your field has both components and your motion has both components, so if your electric field has an X component and a Y component, and your displacement, if you move with both components, then what you get is a change in potential, which accounts for the fact that you move parallel to the X part and you move parallel to the Y part. So this is kind of what we've been using all along. It's just we always set it up so we only have an X part or we only have a Y part. That tends to be the easiest way to approach it. So this is the general result. We probably won't do examples where you have both components and both displacements, but it's good to know that you could do it if you came across it.